Hello everyone, welcome to the seventh lecture of Electronic Devices and Circuits 2 course. Today we are going to start a new topic, that is filters. Filters are a very important class of circuits. Volumes of books have been written on filters, and this still remains a very active area of research. So let's proceed. So filters, as I said, one of the most important circuit building blocks in electronic engineering, and this is indispensable for communication systems. Any communication system will have some sort of filters. Without filters, there are no communication system. And in most instrumentation system also will use filters to suppress noise or to select particular frequency for many different reasons. And what we'll be doing here, our objective is to understand the basic properties of four major filters, learn how to design, analyze, and construct the measured filter circuits, how to draw Bode plot, which is a special technique to draw the frequency response plot of filter circuits. So first, how the filter circuits are represented. We can represent a filter circuit by a two-port network as shown in this diagram. So this has an input port and an output port. It's similar to an amplifier. Amplifier also has an input port where we apply the input Vi, and it will have an output port where we take the output from, denoted by V0. So similar to the amplifier, filter circuits we can also represent by, or it is represented by, a two-port network. The ratio of the output voltage to the input voltage of the filter circuit is called the transfer function, denoted by Ts. What is written shown here? Ts stands for the transfer function. It is similar to the gain for the amplifier, which is also the ratio of the output to input, and we call it gain for the amplifier. But for the filter circuit, we call it transfer function. This is a function of frequency. Filter circuits, they respond to the frequency of the signal. For different frequencies, the output will be different. So it is expressed as a function of frequency. S here is the complex frequency, which is j omega. As you know that for the reactance terms, the inductive or capacitive reactance, we have j omega. We have, for inductor, we have the j omega L. For capacitor, we have 1 over j omega C. So this omega always comes with frequency, omega comes with the j, this complex term. So that S stands for this j omega. That is for convenience of mathematical analysis. The j omega is replaced by S. It's called the complex frequency. So this Ts, the transfer function, is the main thing that represent the filter characteristics. Analyzing the transfer function Ts, we can extract most of the important features of a particular filter circuit. So the types of the filter. So we will focus on four major filter types. One is the low pass filter. Usually we call LP, low pass filters, LP filters. Low pass filters will allow only low frequency signals to pass through, and then we have high pass filters that will allow only the high frequency signals to pass through. And then we have the band pass filter denoted by BP that will allow a certain band of frequencies to pass through. And if you are outside that band, it will block those frequencies. Then opposite to that, we have band stop filters that will stop a certain band of frequencies. If you want to block certain band of frequencies, right, if the signals of those particular band is not wanted, right, if you want to get rid of those signals of certain frequencies, then use band stop filters. So these are the four major filter types that we'll focus on in our studies, how we can construct these filter circuits and how we can design them. So now what is the characteristics, or what are the characteristics of filter circuits? So first we consider the ideal filters. That will be easy for us to understand the characteristics of the filter circuits, the main key points, and then we'll see how the characteristics of those of the practical filter circuits varies or deviates from the characteristics of ideal filters. So characteristics that we are showing here are those for the ideal filters. First, this one is for the low pass filter. You see the low pass filter will allow the signals of low frequency to pass through, and there is a certain cutoff frequency here. It is denoted by omega p. P stands for pass, pass band. So the low pass, the up to frequency omega p, this filter will allow the signals to pass through. So any signal having a frequency from 0 to omega p will be able to pass through the filter circuit. So this is called the pass band. And here transmission magnitude of the transmission is 1, that is 100% transmission. Whatever you get at the input, you get the same at the output, so 100% transmission. And if you exceed this frequency omega p, then the transmission is 0. So that is denoted as, is called the stop band. So that is how the low pass filter, the characteristics. So we have the pass band from 0 to WP. WP or omega p, this is also called the cutoff frequency, which is denoted as omega c. It's the same as the cutoff frequency, which is I think we are more familiar with. Now the pass band is between 0 to omega p, or the cutoff frequency, and we have the transmission magnitude 1, and beyond the pass band, the cutoff frequency, we have the stop band, and transmission magnitude is 0. And here we have the filter characteristics for the high pass filter, which is just opposite to what we have for the low pass filter. We have the pass band at high frequencies, stop band at low frequencies. So any signal with frequencies higher than omega p will be able to pass through the filter circuit, and any signal below that, with frequency below that, will be blocked by the filter circuit. So we have the transmission 100% transmission at higher frequencies higher than omega p, and we have 0 transmission for frequencies lower than omega p. So this should be the characteristics for the low pass and the high pass filters, just the opposite to each other. Low pass will have 100% transmission, or the pass band, at low frequency from 0 to omega p, and for the high pass we will have the pass band beyond omega p, 100% transmission, and below that the transmission will be 0. And omega p here is same as the cutoff frequency, which is denoted as omega c. Now, these are for the low pass and the high pass, and there are two more filters, band pass and band stop filters. So you see that band pass filter will allow a certain band of frequencies to pass through. Here you see that the two pass frequencies are omega p1 and omega p2. If the signal has frequencies within this range from omega p1 omega p2, the signal will be able to pass through the filter, and this is defined as the pass band. So this is the band of frequencies where the transmission is 100%. So within this band, transmission is 100%. And if you're outside that band, outside this band, if frequency is higher than omega p2, or if frequency is lower than omega p1, then transmission will be zero. At both ends, at both low and high frequency, transmission is zero. So this is the lower stop band, and this is the upper stop band, and this is our pass band. And so this is known as the band pass filter that allows a certain band of frequencies. And then we have the stop band, that is band stop filter, that is just the opposite to what we have for the band pass filter. Here we have this stop band that is within these two frequencies, omega s1, the stop frequency, first stop frequency, and the second stop frequency. If your signal has frequencies within this range, then that signal will be blocked by the filter circuit. And if your signal has frequencies outside this band, if it is higher than this omega s2, or if it is lower than this omega s1, then it will be able to pass through the filter circuit at both ends at low frequency, and also at high frequency transmission is high. We have 100% transmission, and within this the band, the transmission is zero. So that is what defines the stop band, and that is the characteristics for a band stop filter. Now the frequencies that here are denoted as omega p1, omega p2 for the band pass filter, and omega s1, omega s2 for the band stop filter. These are also known as the cutoff frequencies. Like omega p1 will be lower cutoff frequency, and omega p2 will be upper cutoff frequency. And for the band stop, omega s1 will be lower cutoff frequency, and omega s2 will be the upper cutoff frequency. So here omega p1 and omega s1, we will usually call them lower cutoff frequency, denoted as omega L, and the omega p2 and omega s2, they are actually the upper cutoff frequency, denoted as omega H. And the difference between these two frequencies, this range, is also known as the bandwidth. So bandwidth of the filter circuit is the difference between these two cutoff frequencies, omega H minus omega L. So these are the characteristics of the ideal filters for the four filter circuits. As you can see that they have very sharp transition. At pass band you have 100% transmission, and in stop band there is a zero transmission. And as you move from pass band to stop band, there is a sharp transition, abrupt transition. It moves abruptly from 100% transmission to zero transmission, and from stop band to pass band, so it moves from zero transmission to abruptly to 100% 100% transmission. So these are the features of the ideal filter circuits, that you will have 100% transmission in the pass band, you will have zero or no transmission in the stop band, and there will be sharp transition, abrupt change from pass band to stop band. These are the main hallmark of ideal filters. The practical filters, how they will differ from these ideal filters. So you see that we are showing the features or the plots for the ideal filters again. Now on top of this we'll show the features or the plot for the practical filters. Now first we show the plot for the low pass filter, a practical one. So if you have a practical low pass filter, the plot will look like this. At very low frequency, at very low, almost zero frequency, you will have 100% transmission. And as the frequency increases, the transmission will start decrease and keep on decreasing. And when you reach the cutoff frequency, magnitude will be actually 1 over square root 2 or about 70%. And as you keep on going to higher frequencies, magnitude of the transmission will keep on dropping, right? And it will keep on decreasing, and as the frequency approaches infinity, it will approach zero. So there is no sharp transition in the practical filters. There is always varies gradually from 100% transmission at very low or zero frequency to zero transmission at very high or infinite frequency, right? And in between there's a gradual change. So in most of the pass band, the transmission is less than 100%. It is not 100%. And also in the stop band, it is not zero. So you have substantial transmission also in the stop band. So these are the features of a practical filter, and that is how it varies from the ideal filter. Ideal filter will have 100% transmission in the pass band, but practical filter will have less than 100% in the most of the band, and ideal filter will have zero transmission in the stop band, whereas practical filter will have much higher than zero. The transmission will be there higher than zero. You have a non-zero transmission in the stop band, and the transmission is the change in transition from pass band to stop band. There's no sharp transition. So that is for the low pass, and high pass is just the opposite. At very low frequency, you have zero transmission, and as you increase the frequency, the transmission will increase and increase, and at cutoff frequency it will reach the magnitude of about 70% of maximum magnitude, and as you keep on increasing, right, it will approach the 100% transmission at very high or infinite frequency. That is just opposite to what we have for the low pass filter. So these are the characteristics. These are the plots for the transmission, how it varies with frequency, what is also known as the frequency response plot for the practical filters, and this is how they differ from the ideal filters. The same thing we can show for the band pass and band stop filters. So we have the ideal filters, and we superimpose on the ideal filter characteristics. On top of this, we superimpose the characteristics of a practical band pass filter. So you see that you have the maximum transmission at the center, and as you move away on either side, it will start falling. And at the zero frequency, you have zero, and the high frequency side, it will keep on decreasing and approach zero at very high frequency. So that will be our frequency response plot for the practical filter. That is how it will vary for the band pass, and for the band stop it will be just opposite. At very low frequency you have high 100% transmission, it will keep on falling, and it will reach almost zero transmission at the center of the stop band, and as you move away, go to higher frequency, it starts rising again, and at very high frequency it will approach 100% transmission. So that is how the filter characteristics will vary for a practical filter from that of an ideal filter. You don't have 100% transmission, or you don't have zero transmission in the stop band and 100% transmission in the pass band, and there are no sharp transitions.